Now, starting today is the beginning of the rest of the course, which means we're going to talk about large systems, ideas, algorithms, techniques, everything regarding large distributed systems. And the first thing I'm going to do is talk to you about something called ΔQSD, which is a way of debugging very large problematic systems. And the company that did this, which is called Sol, it's been developed over 30 years. And before that, it was a research topic in universities. So mainly in the University of Bristol in England. And it has been used to save many big companies. Many big companies have saved billions of pounds or euros or dollars through this. But it was all inside the heads of the people of Sol. Basically, these are the two main guys, Neil Davies and Peter Thompson, and a number of other people. And there were some PhD theses worked around this. And since a couple of years, we're trying to extract this from their brains so that it can be generally used, because it can save a lot of people a lot of effort. And I think, therefore, it's very good to show you guys, because when you go into industry, this will save you a lot of headaches and money and so on. Okay. And so we're going to have 2 lectures on this today and next week. And there will be a department seminar on the 24th at lunchtime, given by Neil Davies. So he's coming to visit. And so this guy is a very interesting guy. He's always telling stories. He knows lots of hidden information that is never published, that you never see in the newspapers. Okay? And he will not say it as long as we're filming it. But if we turn off the video, then you can say it. Okay, so that will be on the 24th, and it's a free lunch. So there will be a message. If you want sandwiches, you'll have to send a mail. But I consider it to be part of the course, because Neil is kind of going to give the wrap-up of this. Okay, but first I'm going to give 2 lectures. Okay, so before we start, a few seconds of respect for the Ukrainians, who are still fighting for their freedom and for ours. And I hope they can keep doing it. Okay, the slides are on the Moodle. This is the full table of contents. So here I'll give some case studies. I'll give you some example. And these are real industrial things. It's not just toy. That have lots of money attached and lots of real things attached to this. And then I'll talk about the basic system, basic approach, and with a number of lots of examples. Okay, how it works. There are some mathematical concepts attached to this. Basically, quality attenuation and outcome diagrams, which are formal things, which I'll explain. And then, this will be for next week. I will go into when you have dependencies. So the real nice thing about ΔQSD is you can predict how systems work when the load is very high. That's exactly when you want to know what's going to happen. If I have a telecommunication system and everybody's calling because there's a natural disaster, then it might break down, okay? But ΔQSD can actually help you avoid that by predicting exactly what's going to happen and let you design it so it doesn't break down, okay? So it's really useful in the hard case. Okay. Okay, first let me give an introduction. I'll give you some general kind of introduction, and then I'll give you some nice industrial case studies to start. Okay, first of all, what kind of systems are we interested in? We're interested in large systems, systems with many, many, many users. This is the kind of system we're interested in. For example, telephone, where thousands, millions of people are calling, or Amazon, where millions of people are ordering things. So many independent users, and we're interested in real-time performance. Okay, really the interesting case. And it's nice when these users are independent, because then you can actually reason about them. And the problem is overload. What happens when the system overloads and breaks down? Now that's really the interesting case. It's easy to make a system that works when the load is very low, but when you have overload, it's much harder. So here's what we're going to talk about overload. So some examples. So these are all examples that have industrial use. Cryptocurrency platforms, distributed systems that do tasks for many independent users. BNSol is actually working for a company called IOG, and they are part of the team that implements the Cardano platform, which is doing the ADA cryptocurrency. So if you buy ADA coins, whatever, then this is the kind of technology they're using. So I'm going to talk a little bit about that. Also, telecommunications. Big companies. Vodafone, since they're in the UK, it's mostly British companies, but not only. It's British Telecom, Vodafone, for example. Client-server systems with lots of clients. Distributed sensor networks. For example, in CERN, where you have networks connecting the colliders to analyzers, and the data is flowing very fast. This kind of distributed sensor network is very easy to analyze using ΔQSD. Okay, so that's kind of what we're interested in. Many users and real-time performance under overload. Okay, so you can see this is an interesting case, huh? I want to say a few words about the company now. That is the main people who developed this. This is called PNSol, Predictable Network Solutions. They're in UK. And they were founded in 2003. People who were at the University of Bristol, which is somewhere in the west of England, or Wales, I don't know, somewhere in there. And they have worked over the years for many large companies, and they have saved a lot of money for these companies. Unfortunately, they only get paid what they are contracted for, but they have saved billions for these companies. So this is a real industrially validated tool. They also work in the United States, Boeing Space and Defense, and IOG is the cryptocurrency company. They used to be called IOHK. HK means Hong Kong. They were in Hong Kong, but for strange reason, they're not in Hong Kong anymore. I don't know if you can imagine why they move away from this great place, but they're not in Hong Kong anymore. I think they're in Singapore now. So they're called IOG. IO, instead of Hong Kong, G means global, IO global. So these guys have a very competent engineering team. And of course, the cryptocurrency is a very demanding area, okay? So high load, scalability, many users, graceful degradation. When the load increases, you want predictability, okay? Predictable under high load. Okay, so that's the context, okay? And so ΔQSD is developed over many years. It didn't appear very suddenly. It took 30 years. Even more because there was some work before. And there's some very nice properties that you'll see when we get into it. It's compositional, means you can bring the bricks together. It's stochastic. It talks about probability distributions. You can also look at partially defined systems. You can actually predict the performance of a system before you build it, okay? And also there are other things, multiple time scales, dependencies, which I talk about next week, okay? So this 2 lectures, I want you to understand the principles. Of course, you will not become really experts unless you actually use it, but at least you get some idea. There's 2 main concepts: quality attenuation, outcome data, which I'll explain. The systems are independent parts. That's how it starts. You assume it's independent and then you add dependencies as you need it. Then you have notions of refinement, so you can start with very vague things and make it more concrete. And then you can compute predicted performance and also infeasibility. If you make a mistake and it's impossible to build a system. Let's say you assume that a component has negative delay. Well, that's not possible. You can actually compute that before you build. Okay? Okay. Before starting the case study, I will explain the two main concepts, and then it's enough to understand the case studies, and then we get into it. There's two main concepts. So if you understand these two, you already have a really good idea. You have one, the one is called quality attenuation, and we're going to write it as delta Q. This is a cumulative distribution function. So it basically gives us the delay, but it's not a number, it's a distribution function. And it's combining delay and failure. So I'll explain that. And the second thing is the whole system. So quality attenuation is like one component, okay? You have a component like database, message going in, message coming out. And there's a delay here. So that's very easy, right? So this delay is modeled as delta Q, okay? That's kind of easy. But if you have a whole system, you have many of these boxes connected together. And in order to do that, you have what's called an outcome diagram. So it's a graph. So it's like, it's related to causality. It's a graph that shows the relationships between all the outcomes. An outcome is just the behavior of one of the blocks. Okay, that's one outcome. But if you have a whole system, you have many of those together, connected together. It can be very complicated. And so this is a directed graph that shows causal connections. And you can compute delta Q from this graph. Okay, so that's the two main things. But that's kind of vague. Let me show you now more concretely the two concepts. So here we have a component, might be database, okay? You give it a query and it replies. That's pretty easy, right? You give a query, it replies. So one of the questions is, what's the delay? If I give the query, how long do I wait between the query and the response? Well, it's not a constant, okay? I mean, it's a number, right? 5 milliseconds. But it's not always 5 milliseconds. Sometimes it's small, sometimes it's more. So it's not a constant. And sometimes there's a problem. Sometimes you get no response. In real systems, that happens. Maybe there's a problem on the network, some kind of weird glitch. You do query and you never get the response. So you have some kind of failure, or network failure, or component failure. So you can't just say it's a number. Okay, so ΔQSD, they make one assumption. They say this delay is a cumulative distribution function. That means instead of just being one number, it's a function. For each delay, it tells you the percentage of queries that have a delay less than or equal to that. Okay, so it's an increasing function. And typically it will increase to 1, okay? Eventually, if you wait long enough, you get response. But it also models failure. Maybe the maximum here is less than 1. Maybe there's 5% of the queries that give nothing. And so it's not technically, mathematically, a cumulative distribution function will go to 1, but this function sometimes goes less than 1. So technically it's called an improper random variable. But you can consider it to be like a cumulative distribution function, but it might stop less than 1. And that's it, okay? So that's not a very complicated thing, but it's not a number, okay? It's more than just a number. It will model all kinds of variability and also model failure, okay? Both the variability and the failure, okay? So I guess this is not news for you. You know what it is, right? Cumulative distribution function. You have seen it. Okay, so this is a cumulative distribution function. Technically slightly different because it doesn't actually end up in 1, but basically you can consider it to be like that. And that's the delta Q. That seems quite straightforward, but we will see the consequence of this. And now we connect them together. So this is just one component, database. But maybe I have many components in my system. So maybe I have a front end connected to the database. So the user does something, clicks on a window, query is sent to the database, and then the response comes back. So I have two components connected together. And my question is, what is the total delay from U1 to R1? So it's basically combining the two components. So I have two delta Qs, one here and one here. And I combine them, I make another graph. So this is this yellow graph here. So I'll always have blue for the system and yellow for the outcomes. So the outcome diagram is just all the delta Qs. Okay? So I have U event here. U event means the U message coming in. An Q1 event is this message going here. And an R1 event is the message coming out. So between U1 and Q1 there's a delay. And that is modeled by a delta Q. And this pair, U1, Q1, okay, is called an outcome. Okay, it's like what you see when you look at the front end. And this one, ODB, is the outcome from the database. And so you're actually combining two delta Qs. So the total delay of the whole system is the sum of the delays of these two. Okay, if this one's 5 milliseconds and this one's 6, then the result will be 11 milliseconds. Okay, that's very simple, right? And we write it like this, using this plus with a circle around it. But it's not actually arithmetic that we're doing, because these delta Qs are functions. So it's more general than just adding 5 and 6 milliseconds, okay? We're adding two distribution functions to get another distribution function. So this is a much more interesting computation. And I don't know if you have seen anything like this in another course. Does the word convolution ring a bell to anyone? Well, those who know about convolution will be very happy, because that's at the heart of this. Those who don't know convolution, I will explain it to you. Okay? But right now I'll just say it's a sum. But it's a more smarter sum than just arithmetic. It's actually doing convolution of these two functions, which is, it's doing kind of a generalized sum. But I'll explain that later. Okay? Okay, so now we know enough to go to the case studies. So the idea is we're going to have a bunch of components in the case study, and each one will have a delta Q, and we combine all the delta Qs, and then we want to debug the system. Okay? We combine the delta Qs of the components, Ci, to get a delta Qs of the whole system. And if there's something wrong with this guy, we can actually reason backwards, like do Sherlock Holmes style reasoning to figure out what was the source of the problem. Okay? So that's the case study. So let me go to a first case study now. Okay? There's many case studies, but I'm going to present two case studies only, because otherwise I would be only doing case studies. I will talk about something called small cells, and then another one called Cardano Shelley. Both of these are actual industrial case studies, okay, done by P&Sol, and are covered by non-disclosure agreement, which means I cannot name the company that's involved here, although that company is very happy that P&Sol saved a lot of money for that. Okay, so in the small cells, I will use delta Q for debugging. So we have a system with a problem, and this big company was very worried, and P&Sol basically solved this problem by deducing what's going on, actually using abduction, if you want to be very precise, to figure out using Sherlock Holmes style reasoning. But in Cardano, which is the cryptocurrency, they did smarter than that. They actually were there in the beginning, so they helped design the system with ΔQSD, so they avoid all the problems from the start. And that worked really well. So the better approach is to use the design, okay? Prevention is much better than cure. You can use ΔQSD for both debugging and designing, but of course it's better if you can use it for design. But let me first explain this one case study. This is called small cells. Okay, let me first tell you a little story. A major MNO is a mobile network operator who shall remain unnamed. So this is a real story, okay? There's a real company hiding behind that, a huge company hiding behind that MNO, but I won't tell you what it is, which one it is. They won't be happy to find themselves on YouTube being insulted, so I will not mention them, okay? So this is a major MNO. They deployed small cells. So small cells are basically the endpoints of radio access for mobile telephones with range 10 meters to 3 kilometers. And they are connected to this backhaul, which basically allows to do point to point. So you have two small cells on the ends with a huge infrastructure behind. Okay. So this company built that, high tech, etc. I don't know, maybe it was 4G or something, some high tech thing. But it didn't work very well. I mean, it did work, but it did not scale. When you had too many users, the voice quality started going very bad. The cells were failing. They were crashing. What's going on? Everything seems perfect. The design was really nice, according to this company. It was really well done. What's the problem? So they were very worried and they couldn't figure it out. So they had, through their connections, heard that there's this company, P&Sol, that can help. So then they called in P&Sol as kind of outside consultant to investigate this. And P&Sol used ΔQSD techniques. They determined the outcome diagram for the whole system. They measured the delta Qs, and they were able to solve the problem. And so diagnostic, and they proposed a cure, and this company was very, very happy after that, okay? Okay, so here's more explanation of what's going on. Here, I have the small cell, some radio connection. Here is kind of like synthetic, this would be like mobile phone, synthetic load generator. And then this is going into the network, okay? But the network is owned by different people. It's not just MNO who is owning it. There is the local, what's called wholesale access network here. Then there is something called the national interconnect. And then it goes into what MNO owns. So there's some layers of stuff before it gets into the part that's owned by MNO. So MNO, so this is called backhaul suppliers. They made contracts with other companies to have some performance and everything, and the other companies were satisfying this, okay? So MNO believed that the contracts with these two companies would deliver the service nicely and contain the hazards. That means there would be no special issues and no residual hazards, so no weird problems that pop up. And they thought that their contracts were very good. They said, we want you to do this bandwidth, and they were providing the bandwidth and everything, it's contract. So they had all these problems, but these two guys were not infringing, okay? They were completely following the contract, and still there were problems. Huge problems, okay. Notice there's delta Qs here. I made some points here, A, B, C1, C2, D, E. So if two people talk to each other, one of them is at point A, and then the message goes all the way into the center, and then it goes back to the other guy, okay? So you get A, B, C1, C2, D, E, and then back D, C2, C1, B, A. Okay? So you see how the message goes, huh? Okay, so PSOL had this system. This was an installed system. It was built, and this big company had spent billions already building it. Okay, so major system covering the whole country. So PSOL put some measurements on there. They had synthetic traffic generator and the reference point E, which is in the center. Huh? So remember, keep this picture in your mind. It's on the slide. Huh? And you add internal observers to get some spatial discernment, so you can actually see what's going on in different places. Okay, so you have an outcome diagram. You go from A to B, B to C1, and so on. So you can see these are outcomes. Huh? If a message starts here and arrives here, that's an outcome, and it has a delay. Also here, it has a delay, and it goes in two directions. Okay, you see what's going on, huh? And these are two separate companies. This is not the MNO, and the MNO stuff is in the center. Okay? See how it's going, huh? Okay. And all these observation points, so there was 4 in the middle, huh? Each one really increases. I'm not sure it's actually doubling, but this gives a lot of information, okay? You have all these delta Qs. Okay, I'm not going to give you the actual information because of the NDA, but I'll give you information that looks the same, okay? First of all, it's going upstream and downstream. When I go from one mobile phone to another, the two A's, huh? It goes from A to E and then E back to A. Upstream and then downstream. First question, is there any direction that has problems? Okay, here is the round trip time variability. Okay, so the system is running, 20 seconds, 40 seconds, so time is ticking, and these are round trip, measured round trip times in seconds, 0.1, 0.2. So you can see there's some variability out. The round trip time is not always the same, huh? It's kind of fluctuating. And you can measure it by going from A to E, and then from E to A. So E is in the center, huh? So here you have the upstream round trip, upstream time and the downstream time. So from A to E and from E to A. Again, the system is running. This is 140 seconds. You can see the delay here. It's varying a lot. But the downstream is less. Okay? So the upstream variability seems to be 5 times higher from A to E than the downstream. And the tail variation means the real extreme things, even 10 times higher. So what do you think? Maybe there's a problem in the upstream. Ooh, no, actually not. The problem was not in the upstream. The problem was actually in the downstream. So the downstream seems not very constant. How can there be a problem? Well, it's not always that there's a problem, okay? Okay. Now let's look at subpaths. Now let's look at messages going around the system, not just how do you say this kind of scatter plot, where we're going to follow messages going upstream from A to E and going downstream. Okay, these two graphs are at the same scale. So this is 0.05 second, here also 0.05, you can't read it, but it's been rescaled, so it's the same scale. So you can see the upstream is fluctuating a bit, the downstream is fluctuating a bit, but here there's this huge peak. Eventually, after some time, there's this huge peak. So what's going on here? Okay, this is from DCB delay. So it's actually the two other companies. It's not even MNO. It's not even their equipment that's having the problem. So this is a problem in the downstream. Okay, so let's focus on that. So luckily we have some more, we have some intermediate points. Okay, internally, we have the national interconnect and the wholesale access. So let me very quickly go back to the, here, we have in the downstream, we have the national interconnect going to the wholesale access. These are two companies that are not owned by MNO. MNO has contracts with them. And they are actually obeying their contract. They're not infringing, and still there's a problem. Okay? Okay, so there's this problem between the national interconnect and the wholesale access core. Okay, so we can zoom in. So let's zoom in on this delay here. Okay, so what is going on here? So here, look at the seconds. 590, so this is second per second. 593, 594, 595. So what happens? At some point, so this is the delay between endpoints. At some point, the delay goes very, very quickly up, and then it goes very slowly down. So this very quick is a small fraction of a second, but this is a whole second. This is 1 second where things are very bad. Okay, each of these guys has a big delay. Okay, so what's going on here? Very quickly getting into the problem, and very slowly getting out of the problem. Okay? As we will see later on in the lecture, this is a typical queue overload pattern. If you have a queue, so a component can actually be a queue, and messages are coming in, and there's a delay. So each of these messages has a delay. Now, if the queue is overloaded, the delay will increase by a lot. But then if the load goes down again, the delay will stay high for a long time. Okay? And we will study queues. Part of the behavior of the delta Q is what it does with these queuing systems. Okay? So there was a queue overload. Very quickly we overload the queue, and then once the queue is overloaded, we're stuck for a long time. The system will behave badly. Okay? So the hypothesis of Piensol was that this was a queue overload problem. Okay? And then they actually made predictions of the delta Q, of the queue behavior. So they basically modeled the queue. So technically it's what's called an MM1K queue, as we will see later. So they modeled the queue, and they calculated what the delays would be using the delta Qs, using a mathematical model, and they could see that it was corresponding quite closely to the measured delay. Okay? What this means is that they kind of verified their inference, kind of like Sherlock Holmes. You make some assumption, and then you look at the consequences, and you can see that it was that. Okay, so that means now they're able to make diagnosis. Okay, a queue is forming in the wholesale access network. So there's a connection between the national interconnect. Let me go again to this picture. Okay, we're going down here, and messages are going in here into the wholesale access network. Here we have a queue. So there's some queuing here. Messages are coming. So this is being overloaded, and the delay is incredibly high. So, but still they're not infringing on their contract. Okay, why not? Well, we'll see why not. The wholesale access network is actually doing the work. Okay, now it is in breach, but it is not infringing the contract. Okay? Okay? So I'll explain why. But in any case, the queue is overloaded, and this delays everything, including the control traffic. So these small cells have some control traffic, and if the delay is too high, they will not like it, and they will maybe fail. If it's too high, So the figures here are way above that. So that's why the small cells were failing, in addition to bad quality. Okay? So the voice quality was, of course, affected with this like 1 second delays. So there was like these gaps. So people say the small cells are breathing, means certain time they don't do anything. Okay? So this, of course, the business case for the big company was very weak now because it didn't scale up. Okay? In terms of delta Q, there's an unmanaged hazards. Okay? The subsystems that are connected together, they don't compose. So basically, you are connecting two components. You have the national interconnect and the wholesale access network. And you have two components that are connected together, and they should compose. That means the behavior of the connected system should be reasonable, okay? But they're not. And the problem is that the two components, the bandwidths were being matched. So that means the bandwidth of this guy was high enough that it will accept what's coming here. This bandwidth was higher than what this one was generating. But those are just numbers. The bandwidths are just numbers. So many gigabits or whatever, or megabits. What they should be matching is more than bandwidth. Is the full CDF should be matched. The whole cumulative distribution function should be matched. Okay? This is what's called quality transport agreement. But they were not doing that. But it was not specified either. Okay? Okay, so that Pinsal then explained that and made recommendations to the MNO. And each big company has something what's called a corporate risk register, which keeps track of risks and opportunities that may affect the corporate plan, so what they want to do. And basically you need to do technical training and so on that make sure that people will do the correct kind of contract in the future. Now, that's what P and Sol told this company, and they were telling me that it's not really clear that the company followed their advice, okay? What they did do was fix the network, but maybe they didn't actually fix the real problem, which is the fact that they were matching the wrong thing when they're connecting components, okay? Okay, so that's the first case study. So you can see how looking at full delta Q is actually much stronger than just bandwidths are matched. Okay, so I'm downloading. I have 400 megabit download rate, and I need to I can accept up to 1 gigabit, so I'm fine, right? No, that's not enough, okay? You have to match much more than bandwidth, okay? So that's one example. So you see, do you get what's going on? You understand the example? So this is a real industrial case study, huh? And it was using the composition of delta Qs. Okay? Okay, let me go to a second case study. This is Cardano Shelley. Okay, so the first case study was diagnosis, basically debugging. The first case study, we had an actual running system and we need to fix it. That's actually not so nice. It's actually better to use the approach to design to avoid the problem. Prevention, not cure. And Cardano Shelley was designed in this one. So this is what I want to explain. This is part of the Cardano blockchain system. And this supports many things, including the AI cryptocurrency. And so I'm not going to give a full course on blockchain. I just want to explain that you have a sequence of transactions which everybody agrees on, and it's like a chain of blocks, okay? And when you add a new block, some node will be authorized to create the block and to add it to the previous end of the chain, okay? And in order for that to work right, that previous block must be known, okay? it must have been copied to all block producing nodes. So this part of the algorithm is called block diffusion. So in order to add a new block, one of the prerequisites, you have to do block diffusion. So the Cardano people, they had some implementation, and they had an initial implementation which has this funny Nordic name called Jormungandr, and didn't really work that well. The performance was not enough. Okay, and this was before p-install was involved. So they were kind of worried, okay, that it was not doing well enough. So they made another implementation called Shelley, and this was done together with p-install and using ΔQSD, which I will explain. And it was used to guide the design. So we were manipulating outcome diagrams, and this one actually did work. And I will give you, explain how that one works later. So in order to explain this one, we need to know outcome diagrams. But at least you get an idea here. Another very interesting thing is that Jormungandr was written in Rust. You've heard of Rust? Shelley was written in Haskell, which is a very high-level functional language. And it's a no-brainer that Rust is faster, right? No, not really. In fact, the Shelley implementation did much, much better than the Rust one, because the algorithm was much, much better. So the current one is actually running in Haskell. Actually, IOG is a Haskell company. Yeah? They have a lot of people developing code in Haskell, and that's actually very nice because it allows them to prove that things are correct, which is important when you do money, yeah? Cryptocurrency. Okay. So this block diffusion algorithm was designed using ΔQSD, and they implemented, and it does achieve an adequate performance. So it's a very large, decentralized, secure, distributed system, okay? So it's not a simple thing. And this algorithm, I will give it later, probably next week, in the second lecture. Okay? So those are the two case studies. So you can get the kind of things we're doing. We're really working on large industrial systems. Okay? But now let me go back and make more kind of course on the basic concepts. So let me say a little bit more about quality attenuation and outcome diagrams and give many examples. I want to show you many examples of how it works. Okay, so going back to quality attenuation. So I have a component here, an A, with message coming in, message coming out, and there's a cumulative distribution function that determines the delay between the two, okay? And it combines three things. So there's a number, okay? So many milliseconds. Of course, it's variable. There's also a chance of failure. The message might be dropped. And there's also jitter, that the delay is not always the same, that it can vary, okay? That's why it's a probabilistic function and not constant. And all three things are in one quantity, so it's like one variable. And so this is actually really interesting. The delay and the failure are combined in one variable. That's something that people don't usually do, okay? And it's very important to do that because there's a lot of trade-offs between delay and failure. If you want to reduce delay, reduce failure, you can increase the delay and so on. But here it's like one variable that combines both of them. Okay? So let me say a little more about that. That's actually a very important idea. Okay? Delay and failure are combined. So it's like one quantity. So this function delta Q is like one thing. Huh? It's one variable that has the value as this function. And we're combining two parts of the system that are usually separate. And it's easy to handle. There's a lot of trade-offs between delay and failure, okay? And one of the lessons, performance and fault tolerance should not be handled separately. They should be together. They're two sides of the same coin. Failure and delay are connected. Failure can be reduced by increasing delay. And there's different ways in the same delta Q. So if you change the threshold, so in this value, there is some maximum delay threshold. If you change that, then you immediately change the failure. It's just a specification thing. Or you can do retrying. If you have failure, you can retry. Of course, that doubles, that increases the delay and reduces failure. But it's just a delta Q computation. So retry is just another delta Q. Okay? So that's one thing, combining delay and failure. Another thing is we can compare delta Qs. So numbers can be compared. 5 millisecond is less than 10 millisecond, but delta Qs can also be compared. Here, the blue one, delta Q1, is less than the black one, delta Q2. It's everywhere to the left and above. So always, the delay of the blue one will be less than the delay of the black one. But it's a partial order because they can intersect. You can actually have them intersect. So they're not always ordered. So it's more complicated than numbers. Okay? And then another thing I want to explain is how do you combine them? How do you add them? The numbers are easy to add. 5 millisecond and 6 gives you 11. But delta Qs are not so easy to add. Let's say I have two components, A and B. I have message M1 to M2, M2 to M3. So delta QA is going from M1 to M2. So it's this delay, so it's here. This is the cumulative distribution, so it goes to 100%. And delta QB is for B, is here, from M2 to M3. But what's the total? What's the combined delta QAB? Well, it'll be kind of the sum, so if this one has a delay and this one has a delay, this one will be actually a little bit more, this red one. But how do you compute this? How would you compute this? Have you seen that in a course somewhere? How would you compute so these are two functions, and the final one is also a function. How would you compute this red function? Do you see how to do that or not? I will explain it to you, but maybe you've seen it before. No, I explain it to you. So it's interesting. This is very important. Now, if these two are vertical, if these two are constants, if this one is always 5 milliseconds, then it will be like vertical here. And this one is always 2 milliseconds, it will be vertical. Then this one will be vertical. It will be 5 plus 2, which is 7. So, but that's actually a degenerate case. If it's constant, always 5, it'll be like a vertical line here, and then you can just add them. But what if it's not? What if there's some probability distribution? Things are kind of spread out. You can't just add them. So how do you do it? Here's how you do it. Okay, so here, first of all, I will take the derivative of this one. This is cumulative, because what I want is the probability density. That means for a certain delay, the higher it is, the more probability I have of its being that. So the area under this whole curve is equal to 1. And the area, if I want to know what is the delay between these two, it's the area under this piece. So this is the probability density function. You've seen that. So A has a density function, and B has a density function, and AB also. Now I want to determine what is the density here. So what is the probability that I go from T to T plus delta T? Well, how likely is a total delay T? Well, I'm connecting A and B. If the total delay is T, then there will be some delay in the first one and some delay in the second one. So the component A will have some delay, which I call delta, and B will have some other delay, which has to be T minus delta. Okay? You see that? If the total delay is T, then if I split it over A and B, I get something like this, with some value delta. And therefore the probability density, it has to have this one and this one. It's an and, And since they're independent, the and is a multiplication. That's probability theory. Yeah? So the density here is the density for A of delta times B of T minus delta. It's the multiplication because it's an and. It has to be T delta and T minus delta. But delta is only one value. Delta can be anything from 0 to T, and they will all give big T. There's many ways to split T into a delta and a T minus delta. So basically you have to sum it over all possible values of little delta. But of course this is continuous, so it's actually an integral. Okay. So this is not a completely rigorous derivation, but you can see where it's going. Huh? So you basically have to do an integral of the PDF of A delta times PDF B of T minus delta, going from 0 to T. So this splits the T in all possible ways, and you add up all the paths. So there's like many paths. In order to get T, you can go through one little delta, another third one, many different deltas, so you have to add them all up. So the probability distribution function of AB is this integral. This is, we could call it the sum of the two. This is a convolution, okay? This is what's called a convolution, and you can see the intuition. It's because in order to get T, there are many possibilities. For all the possible little deltas, there's many ways to get T, and you have to add them all up. So and adding them all up, because it's continuous, is an integral. It's not a sum. If this was a discrete distribution, it would be a sum. But since it's continuous, it's an integral. Okay? So this gives you the intuition of convolution. Is that understandable? What do you think? Are you getting it? Those of you who saw convolution before, did you actually already understand that or not? You did. Good for you. But I'm sure there must be people that did not understand it. But convolution is a very important transformation, okay? Here it comes from combining probability distribution functions, but you see it everywhere. For example, in tomography, where you look at the brain through the rays going in, or in geologic tomography, seismic tomography, where you want to study the internals of the Earth by the seismic waves, you're always doing convolution. Okay, it's very, very common. Also in electronics, in electronic systems, when you have filters and combining linear electronic systems, you are always doing convolution. So it's a very important basic operation. Okay, so it's kind of like the sum of probability density functions. Okay, so you get that? So that's the basic thing. That's something we're going to be doing all the time. So it's important to understand what convolution is. Okay, so let me make a small break now, and then we start actually doing system design. Now that you kind of know what the delta Q is, this delay function, we can use it to design systems and make them so we understand how they behave. And I'll give you a couple of examples of that. We can use delta Q to design systems. Let's start with a very simple system. Okay? A simple system where you have just 2 blocks. So I'm designing a simple system. Okay? Maybe I have a database and a front end. Okay, maybe I have a database, the front end, and I want to design. So I need to know what is the performance of these 2 guys and how they fit. And I will show you top-down and bottom-up design. So top-down means you know the overall behavior and you want to find the components. And bottom-up means you know the components and you want to find the behavior. And we can see this is really neat when the design is infeasible. That means when it's impossible. So we can actually predict when we're doing something wrong, okay? And we'll use a really simple delta Q, a uniform distribution. Okay? Of course, in real life, delta Q can be very complicated, but here's a simple delta Q. This is actually very nice. You start with 0, so this is delay, and in between A and A plus SA, you have basically the same probability density. So the system has some delay in between here, and after this value, it's 100%. So the component has a delay between A and A plus SA. So SA is something I call, is like the spread, what are the variation, okay? And this is very simple distribution, but actually it's a really nice one, and lots of components are kind of like that, okay? Servers will be kind of like, not perfectly, but approximately. So this is really good for back of the envelope. You know, when you want to figure out very quickly whether something can work or not, you know the idea of back of the envelope, you write it down while you're drinking a beer on the back of an envelope, and so you can use this distribution. Of course, if you have really complicated delta Q, then you can't do it, you need a tool, okay? If you need to have a detailed delta Q, you need a software tool. But for simple things, you can use uniform, okay? So let me use uniform now. Here's a simple bottom up. So we know these two components, A and B, and we want to know the behavior of the full system. That's pretty easy, right? We know A has some delay, B has a delay, and we want to know the full system. But convolution is hard. But let's assume uniform, and with uniform it's easy actually. So A has minimum delay little a and a spread SA. B has minimum delay B and spread SB. And C goes from C to SC. So we have something like this. So for A we have something like this. For B we might have something like this. And then the result is combining them. And then we can actually do an approximation. So we add these two, and then we have these two spreads. And it turns out you can actually approximate this one pretty nicely. The C is actually A plus B, so that's like regular sum, but a little bit more than that. It's not quite so good, because you have this spread here, the minimum, so these A, B, so here you will have A plus B, but a little bit more. And then you will have the spread of FC, okay? So you have a little bit more. Because these guys are actually varying between these two values, the minimum delay, if you do the computation, is actually a little bit more than A plus B. It's A plus B plus M. And M, if you make the computation, is the minimum of those two spreads divided by 2. And the spread here, this spread, is actually the maximum of the spreads. It's not the sum, it's the maximum. So if one of these guys has a big variation, the other one has small variation, then this guy will have almost no effect, and the output you will see the big variation, okay? So the spread of the output is going to be the maximum of the two input spreads, and the minimum delay is going to be the sum plus a little bit more. So you can, that's that back of the envelope, huh? You don't need to do so much computation. So that's kind of neat, huh? The delay is just a little bit worse than the sum, and the spread is determined by which one is worst, okay? If B is almost constant time, but A has a lot of variation, then the result will have a lot of variation. And it's actually, the variation is determined by the worst one, okay? If you make the calculation. That's kind of neat, huh? But it's even neater if you use it in the opposite direction. Now, this is actually a really interesting way of using this computation. Let's say I know the overall requirement. So I know how this whole system has to behave. I know what the whole system should do. Okay? And I know B. Maybe B is already fixed, somebody bought it. So what is A then? We have to figure out what is the requirement on A. So if C, the bit overall one, is 50 millisecond, and this one is 30 millisecond, then of course this one should be 20, right? Maximum. But it's not so simple, of course, because you have all these fluctuations, you see? It's not so simple. You have to actually do the opposite of convolution, which is called deconvolution. But if you assume uniform distributions, you can figure out the constraint on A. Okay? A has to be the minimum C minus B minus this little m value. Okay? And the spread for A has to be smaller or equal than the spread for C. It can't be worse. Because if it would be worse, then the whole thing would be worse. Here, A has to be just a little bit better than C minus B. You see? If this is 50 millisecond, and this one is 30 minimum, then you might say we need 20 here. But no! You actually need a little bit less than 20. You need to do a little bit better because of the spreads. See how interesting it is? Now you can actually figure out that A has to be a little bit better than 20, and it depends on what the spreads are. You can figure it out. Maybe A has to be 15 or something. So if B has a very large spread, then A is forced to have a small delay. Okay, a small delay, minimum delay. You see that? So that's interesting, And it works even when you have all this fluctuation and varying stuff going on. And what's really interesting is sometimes you can figure out that things are impossible. Okay, which is called infeasibility. Here, the A, this is the condition on A. Now, if this number is less than 0, then A has to have negative delay, and that's impossible. Okay, so that's infeasible. So that's a condition on A, and if A is worse, if this number is less than 0, then it's impossible to build the system. Okay. So the component A is feasible, means we can actually do it. That means the little a has to be bigger than 0. Negative delay is impossible. If we do the computation, A greater than 0, that implies that there's a condition between B and C, back of the envelope. B has to be less than C minus this little number. Okay? So if B is bad, if B is too bad, then it's impossible to fix. If B is not doing very well, then there's no way we can put an A in there to make the whole thing work. Okay? See, that's interesting, But this equation is not so simple. It's a condition on B, between B and C, but there's a B on both sides, B and SB. But SB, this is usually much smaller, it's easier to compute. Okay? So it's mainly a constraint on B. Okay? Now if SB, which is the spread of B, is very large, then it forces A to have very small delay. If this guy has a lot of variability, it forces the delay of A to be small. Otherwise it's impossible. See that? Okay? So if B is greater than or equal to this number, then the design is infeasible. That means it's impossible. B is just not good enough to get this value. So that's kind of neat, There's no way you can put an A in there to make the whole thing work if B is already not much better than C. okay? And so this is great for designing systems, huh? And you can see it's much better than just adding and subtracting numbers. We're actually doing computation with probability distributions here, so it's much stronger, huh? This is really neat, okay? Now, all this is using uniform, which is an approximation, huh? In real life, the delta Q can be more complicated, but of course, it's very easy for software to compute it, huh? It might take thousands or millions of floating point operation. Who cares? That's easy. So we can use the power of computers to do this, even for realistic, complicated delta Qs. So you can see this is really nice for a system designer, huh? And this is the kind of thing you want to do, okay, when you're designing. So you notice that the top-down one, we're doing the opposite of convolution, which is called deconvolution, which you have seen, right? You have seen deconvolution, the guys who have seen convolution? Have you?
Maybe.
Maybe, okay. Deconvolution is actually much harder than convolution, and it's not always a simple result, okay? But for a software tool, it's okay, you can do it. It can require a huge amount of computation to do deconvolution, okay? So, but that's okay for uniform, it's easy, because we know there's only a few parameters. And for a tool, it's actually not a problem, because computers today are very powerful, and it needs a lot of computation, but the user doesn't care, okay? It's a really good use of computation power to help the system designer. And it gives you really strong result, much better than just adding and subtracting delays, okay? Okay, a final little comment. If the difference between bottom up and top down. We are computing in bottom up, we're computing the known behavior. So we have two known components and we combine them. But in top down, we're computing a requirement, constraint on the component, okay? We know the whole system, we know B, and we can put a constraint on A, or a requirement. So A has to be at least this good, okay? So that's the difference in direction, huh? Okay? Okay, so you can see how with delta Q you can do very interesting kind of inference when you design systems, okay? Now the final one, let me talk about diagnosis, which is like debugging, huh? So this is like the small cells. Consider a bunch of components that are connected like this, and the overall delta Q is bad, okay? Something goes wrong, like in small cells. But we can use delta Q computation to narrow down. We can find the faulty component by binary search. So of course, it's not obvious, because delta Qs don't add and subtract like numbers, okay? So we will have to do convolution and deconvolution to narrow things down, but that's okay. So I didn't mention during the small cell case study, but the mathematical model was done with lots of computation, huh? Combining the delta Qs and doing deconvolution to figure out where the problem is, huh? So that's the kind of debugging you could do also, which is much smarter than just adding and subtracting numbers, okay? Okay, so that's all about delta Qs, but that's still kind of simplistic because we're only combining two components. What if we have a huge system with many, many, many components, and we want to combine them in design? Then we have to look at outcome diagrams. So now we can combine components into full systems, okay? And an outcome diagram, it's basically you're observing the system. Notice it's very different from a UML diagram. Huh? You probably know UML diagrams. Huh? You've seen UML diagrams. UML diagrams say something about the internals. They will tell you what is the class structure. They will tell you what is state diagrams. They say something about how the system is built. But outcome diagrams do not do that. They're purely looking at the system from outside. You make no assumption about how it's built. Okay? So it's purely observational. So it's a really new thing. It's very different from UML diagrams. Okay? But still extremely useful. As we saw, you can determine infeasibility. And of course, it doesn't matter what the components are. The components can be software. They can also be human beings. You can compute the delta Q of humans, which we will do later. Or machines can also have delta Q. Mechanical things, I mean. So, okay, so let me explain now this outcome diagram. So these yellow graphs. So here we have some component, message comes in, message goes out. So the outcome is just a pair. You combine the in and the out, the start event and the end event. So it's a pair saying the system is doing this. With this start, it turns into this end. So it's a system behavior, like a database query gives a result, or a click on the mouse sends a message to a server, or something like that. It's this pair, it's any kind of system behavior. And we observe it. So I don't care how it's implemented. Okay? And there's a causality. So there's an arrow here. R1 is caused by Q1. And there's always a delta Q connecting them. These two are always connected using some quality attenuation delta Q thing. Okay? And we can go connect more of them. So this is a simple example where I'm connecting two components. So I give an input, I do a user click here, I send a query here, and the response comes here. So I have two components, user click, query, response. And this outcome diagram will have two outcomes, and there's causal connection. So Q1 is the result of O1, but it's the start of O2. So there's causal connection between the two, and the overall delta Q is just the sum, the convolution. Okay? And that adds delay and failures. Huh? If this one has 10% failure, and this one has 5% failure, this convolution will show you that the overall system has 15% failure. Okay? It will show you that. Okay, a little bit more technically, the outcome diagram, it's more like classes than objects. It means each time you click, you get a query coming out. So each time you have a U event, you have a Q event. So you can have more than one U event. So each U event is connected to a Q event. And the outcome O1 occurs when you have both U and Q. Okay? And you can have a new instance of outcome. So the outcome is like a class. You can have many instances of it. Each time you have a U event, you have a new Q event. And then another U event, another Q. So you can have many instances of the outcome. Huh? So this diagram, it's more like classes than object. Huh? Each outcome can have many instances. Okay. Okay, so that's the basic idea. Let me show you now a more complicated example. So here's a more complicated example. This is a generic client server. Here I have a user clicking on this computer, and there's a browser, and then the network, and then the server connected together. So there's a whole bunch of outcomes here. Huh? The user clicks. Inside, you're running the browser. So it creates a query. So this is going to some database. Huh? And then it sends the query on the network, and the server receives the query. So that's an outcome. Huh? Query sent, query received. And then the server receives the query and makes a response. So there's a delay. So this 04 is the server response. Then you have a message going back. That's another outcome. Sent, received. Then the browser, receive, process, and then the display displays it. The processor sends it to the display, and something appears on the screen. And here you have human being, which I didn't draw. But you could draw the human being here. So you have this whole loop between the user click and the response. Okay? And each of these steps has their own delta Q, which are not numbers. So the whole delta Q is the addition or the convolution of all those delta Qs. Okay? And you can see if there's some kind of variability, all of this will vary. So you see, this is actually a very powerful way of showing how client-server is behaving. Okay? So this is an example of a more complicated outcome diagram. But we're going to see even more than that. Okay? Let me now, before giving more examples, show you a little bit how to use outcome diagrams to design systems. And it's going to be top-down. So let's say we want to make a system, and you give it some input, and it does some output, like Amazon. I click, and I order a book, and eventually the book arrives in my mailbox. Those can be the two outcomes. Or the money is debited from my bank account, and the book arrives in my mailbox. So it's not just software, it can be anything. And I have some unknown system in the middle, which is the gray circle. And now I want to design my system. Okay, so the first thing is to turn this click into some kind of a request message. And there's some kind of reply that is coming back here. But the middle is still kind of unknown. But the middle might be database. Okay, there might be a database is being requested, and the database generates a reply, okay? And then the reply comes back to the user, okay? So basically, each time we go down, we fill in the blanks, we turn the gray ones into yellow circles, okay? And we can compute the delta Qs using convolution. And it might be feasible or infeasible. Maybe the database is already known, okay? Okay, so there's something sent here, the database, and then you have the database reply coming back. But maybe the performance is not good enough here. And then we have to correct it. We might figure out it's infeasible, and then we have to go back. And this we can do it before actually designing, okay? So here's the general top-down design. Okay, so here I have my system from in to out, and I know what it's doing, top-down. We know delta Q system. So the black is something I know, and I know how long the request will take in the computer, and I know how long the reply will take to process. And then there's this unknown thing in the database in the middle. Okay? We can compute this guy using deconvolution. And maybe it's impossible. Okay? Maybe we want this to be 100 milliseconds, and we somehow, this one has to have negative delay if we compute it. If it is, if it's infeasible, then something has to change. Maybe this has to change. We have to put a faster request. But maybe that's not possible. Maybe the whole requirement from beginning to end is wrong. It has to be changed. Okay? So it's like we go up and down these requirements, making decisions and undoing decisions until we get something reasonable. Okay? And each step of the way, we can figure out the predicted performance. So here's the whole design approach. Okay? So these blue nodes are partial designs. And the roots, the leaves of the tree are completely designed system. And the root of the tree is the unknown system. So I have this unknown system with this gray box, and I make a design decision. I say, I want to put in Cassandra database or whatever. And I keep making decisions until I get a completely designed system. Okay? And each step of the way, I can compute the performance. So if I make a decision D1, Dx, and here, maybe I can already compute it's infeasible here, like we did before. So all these work is avoided. So the ΔQSD lets you compute performance, even if you don't know everything. If you only know partially, you can compute infeasibility early on, okay? Even if you only partly know the system. That's really important when you're building expensive systems, okay? So this is very general, how you design, but I'm going to show you some examples. So here's an example of a cache memory. Okay, what's a cache memory? Here's a system of a cache memory. So the way a cache memory works is a small, very fast memory sitting in front of a very big, slower memory. And when I do a read from the processor, I first check for the address whether it's in the cache. So some of the memory cells will be here. If it is, I return it very fast. If it's not, then I have to read it from main memory, okay? So you see the cache keeps a small set of memory cells that I need very often, and they can read faster. Now we can represent this using an outcome diagram. So here's the thing, I have my read and then a return, but we can represent the cache like this. And we add a special operator. Now we are going to more sophisticated outcome diagrams. The cache makes a decision. It's either in the cache or not. This operator is called probabilistic choice. So let's say 95% of the time it picks the upper outcome, and 5% of the time it has the lower outcome. And the upper outcome is a hit. That means it's in the cache. So we have a hit outcome. 5% of the time it's a miss, but then it has to do a main memory read. So you have this main memory read outcome here, okay? So you send the message to the main memory and the main memory has to read. And you can combine these three delta Qs to get the delta Q of the whole system. So now you can see you can really do more complicated system design. The delta Q of this whole system is actually a weighted sum. You take the hit, you multiply by the delta Q of the hit, and you add the miss ratio times the delta Q of the miss. Now the miss is a convolution, miss plus main, so that's a convolution. But this is just an addition, because you're only doing one or the other one. So it's actually just a sum of two commutative distribution functions. So you can actually do this computation. So you can see with this you can actually predict or design the cache. So here's an example with caches and delta Qs. So let's say the hit, 95% of the time it takes one cycle. The miss, determining is 5% of the time, it's 1.5 cycles. And the main memory read takes 4 cycles, okay, for example. And if you combine those three, using the formula I just gave, it gives you this delta Q. That means 95% of the time, you will have basically a 1, and the rest, the 5% of the time, you will have 5.5. Combining the 3 delta Qs gives the cache memory's overall delta Q. Okay? See, this is nice, huh? I mean, you can compute really the behavior of systems, assuming that you have lots of independent queries. Okay? Okay. I have many more examples, but I want to give you a little bit more of the formal computations that you do. So given outcome diagram, and the delta Q's of all the pieces, we can compute the delta Q of the full diagram. Like here in this example, we have 3 delta Q's here. We have these weights, and we can compute the whole delta Q using this formula, which is a property of probabilistic choice. Okay? So delta Q, remember, this is a function of time delay. It's a cumulative probability distribution. Okay? And there's 4 primitive operations. We saw 2 already. Sequential composition, probabilistic choice, where it's one or the other, like in the cache. But then we have 2 more interesting ones. Last to finish and first to finish. If you want to do timeout, for example, I send a message, and whichever arrives first, the response or the timeout. So this is an example of first to finish. Or if I send 2 requests, and I need to get both of them back, that's the last to finish. So they also have formulas, okay? And the software tool will compute all of these. So let me just give you the semantics of these 4 so you can see how concrete it is. It's just a computation. Okay, so this one we know. You have 2 outcomes connected causally. The end event of A is the start event of B, and the probability distribution is the convolution. Therefore, if you really, this delta Q prime is actually the derivative. You're actually doing the convolution of the probability density functions. So this plus, which is the convolution, is doing the convolution of these 2 derivatives, giving you this one, okay? So convolution is this mathematical operator, which has some properties. Of course, convolution is commutative, It's commutative, but that doesn't mean you can switch the components around. You can't put the database in front of the front end, even though mathematically it's commutative. Okay, and then you have probabilistic choice. So I have 2 outcomes, and when the system executes, it chooses one. It's like non-deterministic choice. Okay, it chooses one with some probability, and there's 2 probabilities. There's the probability P and Q here, the weights. So the A is chosen with P over P plus Q, and B is chosen Q over P plus Q, and so the delta Q, so the cumulative distribution function, is just a weighted sum, in fact. So it's just doing arithmetic on these 2 functions, okay? And then, more interesting, last to finish. This is different. Assume you have 2 outcomes, and you wait for both. In the probabilistic choice, you're only doing one, the other one, not the other one. You only choose one. But here you do both, and you wait for both of them to finish. That means in order for them to be done, they have to be the first one and the second one. So what is the delta Q of this thing? Well, it's the probability that for a time t, it's a function of t, that the delay of A is less than t and the delay of B is less than t. If these 2 are independent, then this probability is the product. Okay, it assumes they're independent. And these 2 are the 2 delta Q's. So basically, you have to do the product of the delta Q's. Okay? And that gives you the last to finish. And the final one, which is a really neat one, is first to finish. So again, you have 2 outcomes, and you're waiting for both, but you're done when one of them arrives, the first one. At least one end event occurs. So how do you compute the delta Q of this? Well, there's a very neat trick. It's a dual of last to finish. When at least one event occurs, which is actually the opposite of 0. It's actually 1 minus the probability that's 0. So the probability that you have 0 end events is this. It's 1 minus at least 1. So that's this right here. Okay, that's 0, the probability. And again, you have a product because these 2 are independent. So the probability of 0, that means for a given time t, the delay A is bigger than t, and delay B is bigger than t. That means you have 0, neither the one nor the other. And it's an and these two are also 1 minus. And if you make the simplification, it's the sum minus the product. It's funny, huh? So you take the sum of these two minus the product, that gives you the first to finish. Semantics, okay? Let me give you now another example. This is timeout. So let's say I have a message being sent to the cloud and a response coming back. But I want to do timeout on this. If I wait too long, I want to have something come back. So when the message is sent, I also initialize a timer. And the timer gives me a timeout here. So basically, I'm waiting for two things. The response or the timeout. And it's the first one that goes through. It's a first to finish. Okay? So here's the cloud response, let's say, QC for cloud. Here's the timeout. It's exactly going from 0 to 1 at the timeout threshold. And if we do this computation here, QC plus QT minus the product, you get this. That means less than the threshold, it's following QC, and above, it's actually timeout, 100%. So the overall delta Q is this, okay? So you can manage timeouts also with delta Qs. It's all part of one variable on the delta Q, okay? So it's neat, huh? I mean, it's a very powerful way of describing systems. Final thing, it's the notion of inverting. So these computations are all bottom up, huh? I know A and B, and I determine the overall. But I also have to go back down. We know the delta Q of a component. We need to find the delta Q of a subcomponent. So for sequential composition, we saw you have to do deconvolution, which is kind of hard thing to do, the inverse of convolution. But for the other three operations, it's also possible. And usually there's many possibilities for the subcomponent, a set of possible delta Qs. That means the software tool has to do a lot of work here. If you want to build this into a software tool for doing design, you have to represent that. So the software tool is not so easy to build. We don't have the software tool yet. We want to make software tool. We don't have it yet. Okay. Okay, so that gives you some idea of how you design with these outcome diagrams. But now I want to go a little bit back down to earth and look at some real typical delta Qs. What do you see in practice? What delta Qs can you see? So, if you have a software tool, you can do any kind of delta Q, of course, no limitation. But some typical delta Qs are always coming back. So a good engineer will know them, okay? So we'll give you some intuition on some of the common ones. And the common ones are Gaussian, uniform, exponential, and I'll explain a little bit. So here's important ones. So one important delta Q is Gaussian. So this is a Gaussian cumulative. So the density function is Gaussian, which you know, right? It's this bevel curve. But the thing about Gaussian is you get Gaussian when you add many independent random quantities. So if I have a lot of random independent things and I group them together, I will have Gaussian, okay? It's good for computing aggregates. A whole bunch of things together, it'll be Gaussian, okay? With a mean and a standard deviation. But still, there's some problems. One of the problems, you have this long tail here. And usually real systems, they don't have the tail very long. So you have the second one, which is uniform, which is a nice one. It approximates a typical component. It's like uniform. So A is the minimum time in the server. Then you have some density, so the time will be somewhere in between A and A plus SA. So this is good for single components. So uniform is kind of used a lot. Gaussian is good for aggregates. Okay? And the actual component, now if you actually look at real components like database or whatever, you have to go to queuing theory. So I don't know if you have seen, anybody has seen queuing theory? You haven't seen queuing theory? A little bit? Ah, good for the ones who've seen it. So I'm going to give you a little bit of discussion of queuing theory. So a component can be modeled in queuing theory. For example, you have a buffer and then a server. So if you model a component, you have something like this. You have a buffer with some kind of slots in it, and then you have some kind of a server that does the work. Okay? And you can have one request inside the server, and the buffer has some size k, for example, which are waiting, requests that are waiting. So if you send messages to the component, one of them will be treated and the other ones wait. So typically this is how components work. Okay? And the server time here, you can model it as exponential distribution. So exponential starts at some time, you have a waiting time, and then you have this negative exponential. So basically, it keeps going, eventually it kind of approaches 1. So the time can take longer, but there's less chance. Most of the ones will be done here, huh? Okay, so you can actually model this with uniform. You take this graph and you take the asymptote here, and this is like an approximation of exponential. It works pretty well, okay? This kind of works. So a typical component, you could model it using a uniform, and it's okay for many cases. A good approximation, okay? And you can also add components together. So the addition is a convolution. Huh? The nice thing about Gaussians is the convolution of two Gaussians is another Gaussian. Okay? So if I have two Gaussians here, with the two means, mu A and mu B, the mean of the convolution is the sum. And the deviation, the variance, well, the square of the variance is the sum of the two squares. So maybe you have seen that already. So the variance is actually the root mean square. It's the square root of the sum of the squares. So the means are added, and the squares of the standard deviations are added. What it means is that the standard deviation is increasing slowly. Because when you have many of these, when you're adding them up together, the sigma c will increase slower than the actual sum. Okay? So the convolution is, for Gaussian, is very easy. You can also do convolution for uniforms here. And now it's an approximation. So here I have a uniform, another uniform. I do convolution. It's not going to be uniform. It's this red curve. It's this kind of curve here. But actually, this part is very small, and this part is very small. So I can approximate it here by another uniform. See, it's a kind of interesting approximation. And this little number n is what we saw before. It's the minimum of the two spreads over 2. And the spread c is actually the maximum. Sorry, the spread SC is the maximum of the 2. And this one starts, it's A plus B plus a little bit more. So you can kind of approximate the sum of two uniforms as uniform. Okay? Okay, so let me stop here. So next week we'll go farther and I'll give you more examples. We'll show you some more complicated examples, and we'll look at how networks can be modeled and how more detail on how components can be modeled, especially when you load. So next week I want to talk about overload. We haven't talked about it so much. What happens when you overload the system? Well, you can model it using ΔQ, and it gives you a really nice way of looking at things. Okay?